You inductively charge an electroscope, but in such a way that even when you move the charged object away from the electroscope's terminal, the foils or leaves will still repel each other. You probably already know that if you hold a charged object, like this negatively charged piece of vinyl, near the terminal of an electroscope, the foils or leaves will repel each other. They move apart, like this. And when you move the charged object away, the foils no longer repel each other. They move back together, like this. But to make them repel each other after you move the charged object away, there's just one small step you have to add. Before going into detail on why it works, here's a quick demonstration. All it takes is your finger at the right time and the right place. The key to understanding this is to understand that normally the number of positive and negative charges on the electroscope are equal, and they stay equal. If there's no charged object around, then they're also balanced out everywhere. Wherever there's a positive charge, there's a negative charge to balance it out, or neutralize it. When we move a negatively charged object near the electroscope's terminal, all we're doing is forcing the negative charges away from the terminal and down to the foils. And they'll stay there as long as the charged object is around. When we move the charged object away, the negative charges return to where they were, and everything is balanced out, or neutral again. Everywhere that there's a positive charge, there's a negative charge to neutralize it. But now let's see what happens if I touch the terminal with my finger while the charged object is near the terminal. We start with an equal number of positive and negative charges and everything neutralized. We then move the negatively charged object near the terminal, and many of the negative charges run away to the foils, causing the foils to repel each other. But then, while still holding the charged object near the terminal, I touch the terminal with a finger. As soon as I do that, the foils come together. Then, when I remove my finger, there's no change in the foils. And lastly, when I remove the charged object, the foils repel each other and stay that way. They don't come back together. Let's look at what happened more slowly. When I touched the terminal with my finger, I added another path for the negative charges to take, along my finger and to the rest of my body. This is called grounding. There were still some negative charges on the terminal, but they didn't want to join the other ones on the foil because the negative charges on the foil repelled them. So for them, the repelling force of the negative charges on the charged object was balanced out by the repelling force of the negative charges on the foils. So they stayed put. But with this new path to take, they are repelled to my finger and away. My body's pretty big compared to this electroscope, so I can handle a small negative charge without making a significant difference to my overall charge balance. But now
Good day, grade 9 science students. Today we're going to continue with our lesson. I divided it up into two sections because it was getting too long. We're just talking about charging by induction. And this is what we're going to do in a lab. Now, to charge by induction, we need to do the following. Bring a charged object close to another object and inducing electrons in that object. What the heck did that mean? Well, the movement of electrons within a substance caused by a nearby charged object without direct contact between the substance and the object. In other words, if you didn't get that, bring a charged object close to another object, don't touch it. And here we have a balloon which is negatively charged, brought close to a wall, didn't touch it. What will happen is that we'll induce a charge on that wall. We will do that because the negative charges in the balloon will push the electrons away inside that wall, away from the balloon. What will be left on that wall is a positive charge. And so therefore there'll be a negative positive attraction. So we can also charge an electroscope by this process, but we also have to involve grounding, which I'll explain in a moment. So a charged object is used to induce a charged object on a neutral object like an electroscope. So in this case, we're bringing a positively charged rod close to an electroscope, which is neutral, and then we're going to ground it. And when we do that, we have, again, first of all, when we bring the positively charged object to that electroscope, the electrons move up towards that positively charged rod. When we touch it with our hand, the electrons will flow into that electroscope because that electroscope was induced with a positive charge. So we induced a positive charge on that electroscope. We touched it, and therefore the electrons flow from our hand into it. So when we ground something, we either remove electrons or we put electrons in. Now, after we remove our hand and we remove that rod, what's happened is that we've added electrons into that electroscope. So we now have a negatively charged electroscope. We brought a positively charged rod close to it. We grounded it, and we created a positively charged electroscope. Now, we can also do the same thing with a positively charged object. But we need to know that grounding is the process of connecting a charged object to the Earth's surface. When you ground something, when I touch it, I'm connected to the ground and I'm adding electrons or removing electrons. It provides a path for charges to travel to or from the ground, my body. And the ground is always considered neutral because it's so large, it contains so many positives and negative charges. If you add a little bit of negatives to the Earth or you take away a little bit, it's so big, it doesn't make a difference. So here we have a negatively charged object being brought close to an electroscope, neutral electroscope. The electrons move down into the leaves spread. What happens next is that we touch that electroscope, and because it's negatively induced, what happens is the electrons leave and go through my hand into the ground, and we are left with, once we remove our hand, once we remove that charged rod, we are left with an electroscope that has lost electrons, so therefore it is positive. So in summary, brought a negative rod close to it, touched it with our hand, removed the electrons, therefore it becomes positive. So negatively charged object, grounded it, it became positive. So this is known as electric discharge. Once an object is charged, the charges are trapped on it until they are given a path to escape. When electric charges are transferred very quickly, it's known as electric discharge. This can be caused by induction. This discharge happens before contact actually occurs. So spark and shocks actually is caused by electric discharge, which is caused by induction. Similarly, lightning is caused by induction. In a thunderstorm, you have a cloud up here. It's got a negatively charged part on the bottom of that cloud, and it actually induces a charge on the ground below it. It pushes the electrons into the ground down, so on the surface of the ground, it's positive. So if you have a building there, it's going to have a positive charge at the top and a negative charge at the bottom of that cloud. Because of the induced charge on the ground, it ends up having an electric discharge, which is lightning. So this cloud discharges its excess electrons along a temporary path to the ground, creating a huge spark. That spark causes the air to expand around it, which is thunder. Okay, so air prevents this from happening because it's known as an insulator. An insulator does not conduct electricity. So air doesn't conduct electricity well. In order for lightning to occur, the charge has to be built up so much that it has to overcome the ability of air to be an insulator. So the electric charge has to be huge. And so at this point, air stops being an insulator and it becomes a conductor, and actually an okay conductor because it ionizes, the air ionizes, and it results in an electric lightning strike, which is very, very strong. So Earth is a donator of electrons or a receiver because it's so large. And that's how it grounds things. If it gets hit by lightning, it's not a big deal because Earth is so large. Okay, so we have electric generators that actually a long time ago, friction machines, we can actually generate electricity through friction as well, which we're going to talk about later. And we got a bunch of different machines that can do this, including the Van de Graaff generator, which uses built to create this charge buildup. And we also have a Wimshurst machine, which I'm going to show you in class, which has two discs that rotate against each other and rub against each other, and that excess charge builds up static electricity, which can be a discharge. So that's it for today's lesson. 6 minutes plus the other video part that I put there, but it's not that long. Make sure you record the important bits, and we'll see you tomorrow. Thank you.